So what I have here is a very cool and easy way to demonstrate and let your students play with the idea of interference. So I just discovered this, and for people that have been using transparencies to teach this might not be new at all, but I think transparencies are super cool. So we have a bunch of concentric circles that represent a spherical wavefront for a source of waves right here in the center. So I printed this template page, and I also printed the same pattern on a transparency sheet. Okay, and if you overlay the two sheets that represent, so basically every circle represents a wavefront, okay, a place where the wave is with the same phase, okay. And this would represent exactly the same wave, since interference happens when the sources of light are coherent. That means same phase. That's why we pass light through a single slit and split up. And you can kind of change the spacing between these two sources of waves and show the resulting interference pattern. The best use for this is to demonstrate double slit diffraction and the resulting interference pattern. Why do you have these equally spaced bright spots? So the two sources of waves basically represents two slits separated by a slit distance. But a little bit on the background of this, like, why is this not a good place to demonstrate the single slit? Okay, first of all, for a single slit diffraction, so you have a coherent light, like a wavefront hitting a tiny little slit. So you can consider every point on the wavefront to be a source of secondary wavelets, according to Huygens principle, right? So you're going to have these spherical wavefronts that are going to emanate for every point, including the edges of the slit. Okay, so to demonstrate this with the transparencies, you're going to have to overlay a source at every point between the slit. Okay, so you're not going to be getting an interference pattern demonstrated with this. That looks like that. Okay, but this is pretty good to demonstrate like what you see from double slit interference, where now the two dots here are gonna represent the two slits. Okay, where each slit can be considered as a source of secondary wavelets. So you can really show the dependence between the slit separation and how far apart the interference maxima would occur. So they're inversely related, right? So the sign in this equation can be approximated as a tangent when the slit spacing is significantly smaller than the distance to the screen. So then basically when this angle theta is very, very small. So when this angle is very small, this sign is roughly the ratio of the vertical distance here to the interference maxima divided by the distance to the screen. So we usually call it y divided by d. Okay, so this, how far away an interference maximum happens, is inversely proportional to d, because they're on the same side of the equation. So when we change the slit separation, you see how the spacing between the maxima gets smaller, and when the slit separation gets smaller, you see how the spacing between the maxima gets larger. Pretty neat. Very cool and very easy. And you can print those. You don't need a projector to actually print them. You can hand one sheet and one transparency to each student or groups of students, and you can let them play.